Okay, let me, I want to start by refreshing your memory on the very first right-hand rule that we got, that Ampere discovered, and then giving you a little shortcut rule that you can use to apply to loops or coils. So you can call this first point that I'm making this afternoon the right-hand rule for coils. Now, it's not a different rule, really. It's just I want to point out something to you that'll allow you to do a little shortcut and figure out the direction of the magnetic field quicker than you can with the old right-hand rule. Remember what Ampere's rule was. Now, let's say we have a loop of wire, okay, and let's make the current go around counterclockwise. Okay, so now what direction is the magnetic field in the middle of that loop? Ben?
Like in the middle, going out.
Yeah, you're right. Because what do? According to Ampere's first right-hand rule, you put your thumb in the direction of the current, and then your fingers will curl in the direction of the field. Well, in the middle of the loop, that will always be coming out of the board. Okay, so the field will be coming out of the board. Now, notice that we could have gotten that same answer by doing something else. What if we just put our fingers in the direction of the current? Then your thumb points in the direction of the magnetic field created by that current. Okay, so that's the way actually I figure out how the direction of the magnetic field that will be produced by a coil of wire. I just wrap my fingers in the direction of the current through the coil, and then your thumb always points in the direction of the magnetic field. Okay, so this is not a new right-hand rule. Okay, you can derive this one from Ampere's first rule. Okay, it's the same rule. This is in effect a specialized case of the Ampere rule for coils. Okay, so only for coils or loops we can say curl fingers in the direction of the current then thumb points in direction of magnetic field. I should say magnetic field inside coil. Make that more explicit. Okay, so that's just an easier right-hand rule to use for coils.
Does that work for anything else, or does it just work for coils?
No, just for coils. Oh, uh-oh. I erased too fast?
Yeah.
Then thumb points in the direction of the magnetic field inside the coil. Okay. And since coils will be used, everywhere in electricity and magnetism now, it's handy to know this little shortcut rule. Okay, now I want to make the second point that I want to make now is something about the actual new law that Faraday discovered. So let's call this point Faraday's law. And I want to make one point explicit that I sort of implied this morning but didn't tell you about directly. And so let me set up a new situation to make this clear. Let's say that we have a long rectangular wire like this that's open at one end, okay, and just shaped as I've drawn it. And let's say we lay a wire across this wire. Okay, so think of this as I'm giving you a top view of this. Okay, so we got this long open-ended rectangular wire, and we lay another wire on top of it. Now let's say that we have a magnetic field that we've set up with magnets that's going into the board here. Okay, so magnetic field into board. Now, this wire that's laying across my rectangle is just free to move, right? Now, what will happen if I start moving it in that direction, if I just start rolling it, sliding it in that direction? Ben, any idea?
Then the current will change. Like,
Yeah, I mean, not right now. Right now, there's no current at all in these wires. Okay, I haven't hooked up a battery. I haven't done anything
will build up.
like that.
Start building.
Yeah, you do get a current. Now, why? Nick? Oh.
Like, is the wire, is it in a loop? Or does it come back?
Well, there is a loop now because it's making contact here and contact here. So there is a loop for the current to go in. But if I just start moving this wire, why would a current start flowing? Drew?
But also, were they both the same metals? The same kind of metal, or the same wire?
Yeah, I mean, you can make them the same or different. It actually doesn't matter in this case, whether it's made of the same metal. But think of it this way. Okay, let me back up a step. Let's say, I mean, I've set up this magnetic field going through my loop here with magnets. Well, let's say I start changing the positions of those magnets. Let's say I make the field through here stronger by moving the magnet closer. Now, in that case, what would happen? Ben?
Just that part of it makes it stronger. But
Yeah, I mean, I've changed the situation now. I'm not moving the wire. I'm moving the magnet closer. Okay, say, making this field through the loop stronger. What's going to happen?
by making it stronger, repels.
Well, it's going to, according to what we said this morning, it's going to induce a current that opposes that change in the magnetic field, right? So how would it do that? Daniel, do you know? Oh, well, if the current flowed, let me see, counterclockwise. Ben?
Well, if it was flowing this way, then
Yeah.
it would sort of push it that way, but if it was flowing this way, then it would bring it in.
Yeah, I mean, if I made this field into the board stronger, okay, I'm changing the field to make more magnetic field lines go through this loop, okay? Well, what's going to happen? That change in the magnetic field is going to cause a current, right? The direction of the current is going to be to oppose that change in the magnetic field, right? So since I'm making it stronger into the board, the external field, the current will flow counterclockwise to create a field out of the board that opposes that change. I think that came out sounding complicated maybe, but remember what this law that Faraday discovered. He's discovered that current will flow in loops in order to oppose any change in the magnetic field through the loop. Okay, that was his basic discovery. So applied to this case, if I increase the magnetic field through this loop, current will start flowing to create a magnetic field that opposes that increase. Okay, so it's got to flow counterclockwise. Okay? Now, so that's one way to get a current flowing counterclockwise, is to increase the strength of the magnetic field through the loop. Now, there's another way, it turns out. What if I move this wire? What has happened to the total amount of magnetic field through the loop if I start moving this wire? It's getting bigger, right? Not this time, not because that you've changed the strength of the magnetic field anywhere inside the loop, but you've made the loop bigger just by moving the wire. And so there's more field going through the loop. Turns out that has the exact same effect as changing the strength of the field. That if you make the loop bigger, and so there's more magnetic field going through the loop just because there's more area, that also changes the total amount of field going through the loop, and a current will be induced to oppose that change. Okay, so it's not, the key thing here is not just the strength of the magnetic field, but it's also the area of the loop. What Faraday discovered is that it's the product of the two that really matters here, and he defined a new term to capture that. It's, well, the usual symbol that's used to designate the strength of the magnetic field, like I designates the electric current, right? Well, magnetic field is usually designated by B. Now, Daniel obviously doesn't like that from the expression on his face. But again, it's one of these cases where we're starting to run out of letters, right? Because if I call it M for magnetic field, well, that seems to make sense, but M is mass, right? So we can't use the... Yeah, they could have done that, but They didn't. So we're stuck with B. Maybe in some other language, the word for magnetic starts with B. I don't know. But seems unlikely since the word comes from Magnesia in a province. Okay. So we call the magnetic field strength B. Now, if we call the area of the loop A, so A equals area of loop. I assume Daniel approves of A standing for area. Okay. Then Faraday defined this new term, which is what he called the magnetic flux through the loop. And we're going to use a Greek letter phi to stand phi sub b for that. A flux is the magnetic field strength multiplied by the area. BA, yeah. So now we have one term that captures both of these factors that turn out to be important that Faraday has proven are both important in creating this new effect that he's discovered, the magnetic field strength and the area of the loop. And the way you think of this flux is, the way Faraday thought of it is, he always thought in terms of these field lines, right? So, if you have a bar magnet, say North Pole, South Pole, you know that the magnetic field lines go out from the North Pole and into the South Pole. And he always thought in terms of these magnetic field lines. Well, you can think of this flux that he defines as like the total amount of magnetic field lines going through the loop. So that immediately keys you in that there's going to be two things that are important. The total magnetic field going through the loop is going to depend on the intensity or strength of that field and the total area that field covers through the loop. Okay, so that's flux. Now, and what Faraday discovered, his basic law, and I'm not going to give it to you quite in its full glory, but I'll give it to you, give you a simplified version. Let's just write it in words. The rate of change of magnetic flux through a loop is proportional to the current generated in the loop. Now remember that magnetic flux, okay, by itself doesn't do anything, right? I mean, if you can have a ton of magnetic flux through this loop, and as long as it stays constant, it doesn't create any current at all. Okay, so it's only when the flux is changing that it creates a current. And what Faraday discovered, I mean, the quantitative law that he discovered is that the rate of change of the flux is directly proportional to the current that it produces. Okay, Nick.
Have there been any theories of this, like electricity? Like any more new theories?
Oh, new theories like Franklin's theory. Well, it's getting more complicated now, because notice that in addition to this electricity that actually flows through these conductors, okay, that's Franklin theory just talked about the electrical fluid. But in addition to that, now we have these fields, right? Which Franklin didn't know anything about. So, and we have fields, changing fields that can create currents, and currents that create fields. So, I mean, to this day, I don't think we have a complete physical understanding of what's going on. Physicists are still working on that. So, if you work that out one of these days, you'll get famous for doing that. Oh yeah. Let me see. What does a Nobel Prize pay these days? It's got to be at least a couple $100,000. So maybe you could pick up, say, $250,000 for figuring out a real physical interpretation of what these fields are and coming up with a new theory.
Did
Nick.
scientists get paid for their discoveries?
Oh, well, Faraday made a decent living. He became a sort of the chief scientist at one of the Royal Society's head lab in London. So I mean, scientists didn't make a lot of money back then. It's not like the guys who were building railroads or running major businesses obviously made much more money. But Faraday made a decent living. Okay. So let's sum up what we know now about this new discovery of Faraday's. And let me let's think about different ways to change the flux through a loop. So let's say we have a loop and a bar magnet. Now, one obvious way to change the flux through that loop, well, somebody tell me. JJ, if you wanted to generate a current in this loop, what would you do? Yeah, move the magnet. I mean, that's certainly one thing you could do. Let's say we move the magnet toward up toward the loop. What current is going to be generated? Exactly right. Wait, no. Clockwise. Well, if you're looking from the bottom, if you're looking from the top, clockwise, right? You're looking, because it would flow around. Would flow around this way in order to clockwise in order to oppose the change, because you're increasing the field through the loop by moving the magnet toward it from the bottom, right? So looking from the top, the current would flow clockwise. So that's one way. So one way to generate is to move a magnet relative to a stationary loop. Okay, what's another way? Same setup now. Oh yeah, you're right. Let's say we just take this loop and rotate it. Okay, what is going on in that case? I don't move the magnet at all.
Is that a west or a north? A magnet.
Oh, sorry. There is no west on a magnet.
I know.
It just looked like a W. Huh? Okay, that was a sloppy N. Now, what happens if, now the north pole of this magnet is down below this loop, okay? And instead of moving the magnet up through the loop, I start turning the loop. Well, what will happen? Well, is the flux through the loop going to change? Yeah, because, well, see, originally, it's hard to visualize, I guess. But, I mean, let's say I have the magnet. Okay, I'm going to use this front desk. This felt marker is my magnet with the North Pole up. Okay, and I have a loop above it here. Okay, now at first my loop is horizontal. Okay, so the magnetic field from this magnet is going right through the loop. Now what happens when I turn the loop sideways? It's not going through the loop at all anymore, right? So there's no, I mean, I've gone from a situation where there was all this magnetic flux going through the loop, right? If I turn the loop sideways, suddenly there isn't any.
So it changes constantly.
Yeah, and then I change it some more. I turn it another quarter turn. Now the magnetic flux is going through the loop again, right? So every quarter turn, it's going, a maximum amount of magnetic flux is going through the loop, or no magnetic flux is going through the loop. So it's constantly changing, and that's constantly going to generate a current opposing that that change in the flux. Now, what actually that's so B would be yeah, so let me see. Rotate the loop and now what will this generate a AC or DC current? AC, right, because in fact we could even figure it out. Maybe that would be useful. If we have okay, now we start out with a case where the loop is flat and there's a maximum amount of flux going through the loop. Okay, now let's say we now turn the loop sideways. Well, I mean, so it's yeah, it's vertical, right? So there's no more flux going through it. Now, what's the direction of the current that will be induced from that? Can you figure it out? Okay, it's going to oppose the change, right? The change is to decrease the magnetic flux going through it. Ben. Okay, so let me. I haven't figured it out yet. So let me. It's going to see as we look down from the top. It has to go counterclockwise. Okay, see this a current in this direction. Okay, a counterclockwise current would add to this field, right? That's already going through the loop. Does everybody see that? So that's what it's going to want to do. As you turn it vertically, you're decreasing the flux through the loop. Okay, it opposes any change. So it's going to want to induce a current that increases that flux through the loop. So the current in this case would actually go counterclockwise as you decrease the flux. On the next quarter turn, you would be increasing the flux. So the current would start going in the other direction. Okay, so that is the. Now I had one other simple way to change the flux in mind. C, what else could you do in this simple basic situation? We've tried moving the magnet. We've tried rotating the coil.
What about if you go like that? Like this.
Yeah. Well, you could just move the coil, right? Move it straight down. I mean, rather than rotating it, just move it straight down toward the magnet, say, or away from the magnet.
But isn't that exactly the same as A?
It's really the same as A, because what matters is the relative motion. You're absolutely right. And what Faraday found is exactly what you would expect, that it is just the relative motion that matters. It makes no difference whether you move the magnet, or say you move the magnet up, or you move the loop down. Both things will produce the exact same current. Okay, so move loop relative to magnet. So as Nix points out, A and C are really the same. All that matters is the relative motion. But you can move either one and get the same effect. Okay. All right, we just have, let's see, we have 5 minutes left.
Let's get out early.
Well, let me tell you about one neat thing that shouldn't take me too long. Oh, right. I was assuming that you just had a fixed loop. But yeah, absolutely. I mean, that was what I pointed out. Mr. Van Dam just points out that if you had a way to make the loop bigger, that would also induce change the flux and therefore induce a current. So that was what we illustrated with that sliding wire on the rectangle. Now, here's one neat application of this effect that Faraday discovered. See, I haven't talked too much about resistance to electric current, right? But I remember I told you that it's a bit like electricity flowing through a wire is a little bit like water flowing through a hose or a pipe. And there's always resistance to such flow, right? If you made a pipe real narrow, you'd have a harder time forcing the water through it, right? It's the same thing with electricity. If you make really thin wires, the resistance, what's called the electrical resistance, goes up. If the longer the wire is, the more resistance. So scientists found that all materials have a certain electric resistance, and some of them have less resistance than others. That's why copper wires, for instance, are used, is because electricity flows more easily through copper than it does through, for example, iron. So scientists made studies to find out the electrical resistance of various materials. Now, they also found out that the resistance depends on temperature. So they started studying that. And much later than the period that we're talking about, scientists discovered an absolutely amazing thing, that if you decrease the temperature enough and make certain materials really, really cold, electrical resistance disappears altogether. Okay. This is called superconductivity. And for example, if you take something made of tin, okay, a big piece of tin, if you cool it down to hundreds of degrees below zero, down to 4 degrees Kelvin, okay, yeah, that's the absolute temperature scale. So, and we talked a little bit about that last year, but it's so the bottom temperature on that scale is 0. Okay, it turns out 0 corresponds to something like minus 460 on the Fahrenheit scale. Okay, you can't get any colder than that. Okay, but if you're 4 degrees Kelvin above that, at about that temperature, all the electrical resistance in tin disappears. So current can flow freely without any resistance at all. So, yes?
What metal gives the most resistance? Tin?
Oh, the most resistance. It depends on temperature, but yeah, I don't even know which metal would be the worst conductor. But here's an amazing thing that I'll tell you about. Let's say that we have a bowl made out of tin, and we've cooled it way down to 4 degrees Kelvin. Now, what's going to happen if we take a bar magnet, say, and try to lower it into that bowl? Now, as you lower it into the bowl, well, the electricity can flow freely in this bowl, right? Now, it's going to oppose that change in the magnetic flux into the bowl, right? So it's going to actually, as I've drawn it here, the electricity is going to start flowing around this bowl counterclockwise in order to oppose that increase in the magnetic field. Yeah, that increase in the flux, exactly. Now, that flow of electricity creates a magnetic field going in the opposite direction, which will exert a force on that magnetic pole, right? Push it out. It doesn't want it to come into the bowl. 1 minute. So the bottom line is, if you can take a bar magnet, put it over this bowl, and it'll just hover there.
It won't touch the water?
Oh no, there's no water. This is just an empty tin bowl. You can let go of it, and it'll float over this bowl.
Will it move, like, will the north align with the north and south and stuff?
Then.
What if you put on a suit of magnet, like armor, magnet armor?
Yeah.
You float, there's like a giant.
Oh yeah, absolutely. In fact, people have thought of making trains move in this way. These are superconducting trains. The only problem with this technology is you do have to cool the rails, the train rails, down to, minus 450 degrees, which is pretty cold. But other than that, you can just have a train then float across the rails with no friction at all.
They also use
Yeah.
magnets, though. That's what they're using now.
Yeah.
They have, like, magnets around it.
Yeah. So this is why it all comes back to Faraday's law. That's why it works.